Welcome to a crash course in twin-delayed deep deterministic policy gradients, or TD3 for short. This is a very brief lecture that's going to cover the fundamental concepts and implementation notes for our coding tutorial which will follow this lecture. If you want the full details of how this algorithm works, I highly recommend you read the paper titled Addressing Function Approximation Error in Actor-critic Methods. It's very well written, very technical, very detailed, and it covers significantly more detail and depth than I will do here. I'm just going to give you broad strokes and some idea of what we're going to be doing in our coding tutorial. And we're going to be using TensorFlow 2, by the way, for our coding tutorial, so make sure you have that installed. So TD3 exists to deal with a fairly straightforward issue. How do we deal with overestimation bias in continuous action space actor-critic methods? If you're not familiar with overestimation bias, it is a tendency of agents to incorrectly estimate the value of a state on the high end. So it says this state is worth more than it actually is. And this is a problem because the agent will attempt to access that state in the future, which leads to a suboptimal policy because there are other more profitable states out there. So this is a pretty big problem, particularly when you're trying to approximate the agent's policy, as we are in actor-critic methods. But it's not clear where this would even come from. In Q-learning, we get bias because we take a max over our actions in our update rule for either the table or our deep neural network. So there's some maximization or overestimation built in right from the beginning, and that's pretty easy to see. But there is no max in our update rule for actor-critic methods, so what gives? Where could this overestimation bias come from? Well, on a somewhat theoretical level, I kind of argue, they don't do this in the paper, but the way I think of it is that we have stochastic gradient ascent where we're attempting to maximize the product of our probabilities, our policy, and the rewards or returns the agent receives over time. So there is some implicit drive to maximize score over time, and so when you get natural variation in your rewards or in the trajectory through the state space, you can end up with some incorrect estimations of the values of states because of natural, high variance, which is typical for deep reinforcement learning problems. However, more fundamentally, overestimation comes from approximation errors. Now, this isn't something they prove in the paper because this is a result that dates all the way back to the early 1990s when people were just starting to talk about Q-learning. And so it's been known for a while, but the basic idea is that when you attempt to use some mathematical apparatus to estimate a function in a high dimensional space, you get approximation errors, and that results in overestimation. Now, what is our source of overestimation or approximation error? In this case, it's going to be a deep neural network. Neural networks are, of course, universal function approximators. Mostly, there are obvious exceptions, discontinuous functions they can choke on, the function has to be differentiable and all that good stuff. But for all the stuff we deal with, neural networks are going to be a universal function approximator, and so that leads to a source of error. Now, this is inherent to any approximation method, either tiling, binning, anything like that. So it's not that neural networks are bad, it's just whenever you have a function approximation, you're going to have some error, okay? Because you don't have an infinite amount of time to collect an infinite number of samples to get infinite precision. You're always going to have to lop off your estimate at some point where there are more decimal points waiting for you, should you be able to collect more data. Worse yet, actor-critic methods are bootstrapped. What this means is that we're going to be using our initial estimates to perform updates to later estimates. And so you have some errors in your early estimates that propagate to your later estimates over time. So you get an accumulation of error over time. Now, naturally, there are other ways of dealing with this, and in fact, double Q-learning uses a rather ingenious solution. They use, in that algorithm, two different Q networks, and you alternate their use in the update rule. And so you're never taking a max over actions of the same network that you use to choose an action when you're trying to update the value of that action. And so it seems like it's a reasonable thing to try, so in particular, that's what they do. Now, I want to point something out that in double Q learning, deep double Q learning, they use a not exactly analogous solution to the tabular case of double Q learning. They use something slightly different, which doesn't work in actor-critic methods as they detail in the paper. They're going to use a more exact replica of the tabular versioning of double Q learning. And they're going to perform a slight modification where they're going to clip the inputs of the actions to the Q networks, the double Q networks, which is going to tend to underestimate, and we're going to be taking a min. So later on you'll see in the algorithm that we're going to feed some clipped actions to our Q networks and then take the minimum. So whatever the minimum value is, we're going to take that, which tends to underestimate. Now you may say, Dr. Phil, isn't that a problem? Not really, and the reason it's not a problem is because if we underestimate actions, those actions become less attractive to the agent, and so it's not likely to take those actions again, and so that kind of dampens that out over time. It's a natural feedback mechanism to deal with that issue, so that is rather nice, and it's baked right into the algorithm. The other innovation is that they're going to delay policy updates to give the critic network time to converge. So the policy network is a very slowly changing function, whereas the Q network can change much more quickly. So you have two different time scales there, and that's where the delayed part comes from. Another innovation is we're going to use target networks for the actor and both critics. Since we're doing an analog of double Q learning, which uses two Q networks, it stands to reason we're going to have two critics, and we're going to have target networks for all the things. So we're going to have an actor, a target actor, two critics, and two target critics. So a total of 6 deep neural networks. We're going to have all the neural networks in the world. The other thing we're going to need is a soft update to the target networks. So you have a couple of options for updating the weights of your target networks. One is you could do a stochastic gradient descent on those directly. Another option is to take the parameters from your online networks that you're actively performing gradient descent on and copy those to the target networks directly. Or a third option is to do some slowly varying interpose between the two. So you're going to update the online networks every time step or every n time steps in the case of the policy, and then you're going to do some slowly changing update to those target networks, and that'll introduce an additional hyperparameter called tau to our agent, which you will see later. So this is an actor-critic method, and we're going to have actually 6 distinct. I have a typo there. Sorry, I can't count despite having a PhD in physics. So we're going to have an actor, 2 critics, a target actor, and then 2 target critics, as I said. The purpose of the critic is to be critical. It is to evaluate the values of state and action pairs. So it says, hey, in this particular state, we took some action. I think this was valuable or not. And that will help to update the agent's estimate of the values of those pairs and to choose better actions for given states over time. The actor will decide what to do based on the current state. And it's important to note here that our deep neural network is going to output action values, which are continuous numbers, not discrete numbers, not probabilities. Now that makes this a deterministic algorithm. That's where the name of the algorithm comes in, twin delayed deep deterministic policy gradients. It's an extension of deep deterministic policy gradients. And so we have a bit of a problem there because we're dealing with approximation, right? We're approximating a Q function, we're approximating a policy, we're approximating all the things, and we never know exactly how accurate our approximations are. And so we never know if we are correctly evaluating states and action pairs. So we never know if, given some state, if this action is really the most beneficial action we could possibly take, or if there's some other more beneficial action out there waiting to be discovered. That is called the explore-exploit dilemma. Do we explore suboptimal actions or exploit what we think are the most beneficial actions? And the extent to which you engage in those two activities is the dilemma. And there are a number of solutions to that. Deep Q learning uses epsilon greedy action selection, where you just take random actions some fixed proportion of the time. But in this case, we're going to be adding noise to the output of our actor network when we decide what actions to take. The update rule for actor looks a little bit scary, but it's actually not. So This is the update rule from the paper. J is going to be our loss function for our actor. It's a function of phi, the parameters of the policy network. And you want to take the gradient of the cost function with respect to the parameters of the policy network. And it's given by 1 over m times the sum, or a mean, an average. So our loss function is going to be a mean, and it's going to be the product in this particular equation of the gradient of the first critic network with respect to the actions chosen by the policy network multiplied by the gradient of the policy network with respect to its parameters. Now, this looks intimidating, but it's actually not. This is the application of the chain rule to the loss function. So they have taken the gradient of the loss function with respect to phi, but the loss function is proportional to the output of the first critic network. Of course, the first critic deep neural network has its own set of neural network parameters. It doesn't have an explicit dependence on the neural network parameters of the policy network. So it's very difficult to take a gradient, right, of something that doesn't depend on something else. So the dependence is implicit. It comes from the fact that those actions are chosen according to the output of our policy network. And so you have to apply the chain rule. In reality, all we're going to do is the following. We're going to randomly sample states from our memory. We're going to use our actor network to determine actions for those states. So we're not going to be using the actions from our memory. We're going to figure out what actions the agent thinks we should take now. We're going to plug those actions into our critic and get some value, specifically the first critic, never the second, only the first. That's just by design. And then we're going to take the gradient with respect to the actor network parameters. Now, we don't have to calculate that gradient. TensorFlow is going to do it for us. We just have to do the first three things, where we sample states, use the actor to determine actions for those states, and plug those into our critic along with the states to get some value, and then take the gradient with respect to the actor network parameters. Now, keep in mind that this update isn't performed every time step. It's performed every other time step. How often you perform it is a hyperparameter of the algorithm, but it is not every single time step. Now, nominally, the update rule for the critic is a little more straightforward. So again, you're going to sample a batch of transitions from your memory. You're going to put the new states that the agent observed after taking some action through the target actor network. That's that a tilde parameter there. And then you're going to add in some clipped noise. It's just going to be a normally distributed noise with mean 0 and some standard deviation, something like 0.2. And we're going to clip it in the range of minus 0.5 to positive 0.5. So that's where the clipping comes in for our double Q learning. And the actual double Q part comes in and when we calculate our target's y. So we're going to take the reward that we sample from our buffer and add it to the product of the gamma, which is the discount factor, 0.99 or so. And we're going to take the minimum of the output of the two target critic networks. So we'll say we're going to feed the new states and those clipped actions through both target critic networks. And then we're going to see which one is the minimum and take that for our target value. And then we're going to input that target value into our loss function. Again, you have a 1 over n multiplied by sum, multiplied by something squared. That is a mean squared error. And it's the mean squared error between that target y and the output of both of our critic networks. So our loss is going to have two different components. It's going to have a loss for critic 1, where you have q sub theta sub 1, and then it'll have a loss for q sub theta sub 2. So we'll have two losses. And in TensorFlow 2, when we do our gradient tape, we're going to have to pass in the persistent equals true flag to our function call so that it keeps track of network parameters between gradient ascent steps. And so the rest of this verbiage is just kind of the verbal description of what we want to do. It's going to be much easier once you see it written in code. I assure you it's not that difficult. Next, we have to handle the question of target network updates. So at the very beginning, in our constructor for our agent class, we're going to go ahead and initialize actor, two critic networks, and then a target actor and two target critic networks. And when we first start out, we want to initialize those target networks with the exact values of online networks. And so we're going to have a special case in our target network update function that handles the very beginning of the program. Every other time step, we're going to use the following expression to update the weights. So on the left side, you have theta and phi prime, where the I on the theta denotes either critic 1 or 2. Phi is the parameter for our critic network, policy network, and the thetas are the parameters for our critic networks. And so you're going to multiply tau, some small number, 0.005 in this case, by the values of the current online network, and add in 1 minus tau times the old values of the critic network. So it'll be a small number multiplied by the current values of your online networks plus something that's almost 1 multiplied by the old values of your target networks. So it's going to be a slowly changing update to our target networks. Other thing to note is that we're only going to be performing this update when we update the actor network. So it's not every time step. In this case, it'll be every other time step. Very, very important. So for this program, we're going to need a number of data structures. We're going to need a class for our replay buffer, the agent's memory. Now, I like to use NumPy arrays. It is not the best way or the only way to do it. It's just my preferred way. So follow along with me in the tutorial, do it that way, and then when you play around with the code later to understand it better, go ahead and rewrite the replay buffer to something that makes more sense to you. That's a great way to get started with modifying the program, is with the replay buffer. Next, we're going to have classes for our actor network and our critic network, and those are of course written in TensorFlow 2. We'll have another class for our agent, and that is really going to tie everything together. It's going to have a memory that keeps track of transitions. It's going to have an actor, 2 critics, target networks for each of those, a function to choose an action based on the current state, a function to learn that performs the update rules we just went over, an interface function with its memory that I call remember, just to store transitions in the agent's memory, as well as functionality to save models and perform target network updates, which I forgot to write here. Finally, we're going to need a main loop to train and evaluate our algorithm. So we're going to be using the OpenAI Gym and the Bipedal Walker in particular, because this is a kind of difficult environment for other algorithms. It's a continuous action space with a pretty large state space. I think it has 24 different components in the state space, if I'm not mistaken. Some relatively large number. So it's a bit difficult for agents to learn. And in fact, it's going to take my computer around 6 or 7 hours to complete the evaluation. I'm filming this after I do the code. So it'll take a while to run. So if it takes forever on your computer, don't panic. That's normal, quite normal. So all that out of the way, let's go ahead and get started in the coding portion of this tutorial. All right, so we begin as usual with our imports. We will need NumPy, the base TensorFlow package. We will need TensorFlow.keras. We will need layers. Import dense. That is for constructing our deep neural networks. And we will need our atom optimizer for the gradient descent. And we will need OS for file joining operations for model checkpointing. Let's start with our replay buffer class. Now this should be very familiar to you if you're used to deep Q learning. We'll need a max size, input shape, and number of actions as input to our constructor. Now remember, we're dealing with continuous action spaces, so this number of actions is really a number of components to our continuous action. I just name it that for consistency with my deep Q learning code. So we will save the appropriate member variables. We use a memory counter instantiated at 0 because our memory is finite. We'll need our state memory, which we'll initialize as zeros, and the shape mem size and star input shape. The star idiom just unpacks an array, in this case, whatever the shape of our input dimensionality is from our environment. We'll of course need a new state memory, and that's the same shape. That keeps track of the new states that we are going to see. An action memory. And remember, of course, again, number of actions is number of components to our action. reward memory in the shape of memory size, and a terminal memory. We're going to use numpy bool as our data type. That'll keep track of our terminal flags, the reason being that the value of the terminal state is always 0, and so we keep track of the done flags from our environment to accommodate that. So let's store a transition that takes the state observed, action taken, reward received, new state observed, and terminal flag received as input. We want to know what the first available memory position is, and that's memory counter modulus mem size. That is a property that it will overwrite earlier memories with newer memories as soon as the memory fills up. And then go ahead and save our variables. We'll state underscore terminal memory, and that's all of them, I believe. And very important, we want to increment our memory counter by 1. Next, we have to handle the function to sample our buffer, and that'll just take a batch size as input. We want to know what the position of our maximum filled memory is, and that's given by this minimum of mem counter and mem size. Because we don't want to sample zeros, we initialize our memory with zeros, so if we just sample the entire buffer, then we're probably going to end up sampling zeros until we fill up that buffer, which is totally useless. So then the batch is going to be a random choice from 0 to max mem in shape batch size. Then go ahead and dereference our variables. And dones. All right, that wraps up our replay memory. That's very, very simple. Probably the most straightforward class in the entire project. Next, we're going to move on to our critic network. And that will derive from keras.model, so we get access to all of the properties of that particular base class. That'll help with using the gradient tape for learning later on. We're going to take some inputs for the number of dimensions for the first and second fully connected layers, number of actions, again, number of components, a name for the purpose of model checkpointing, and a checkpoint directory. We will have to do a make directory on that before you begin, otherwise you will get an error and it will not work. Let's call our super constructor and start saving stuff. Do I need to do that? Yeah, why not? So the purpose of the name is the fact that we're going to be saving target networks as well as regular networks, and there are going to be 2 critics, so we want to be able to keep all of those straight when we handle model checkpointing. So we'll save our model name, checkpoint directory, and the checkpoint file. And I like to append the algorithm name to the checkpoint file so that if I do everything in one working directory when I'm experimenting, all the names tell me exactly which file correspond to which algorithm. You don't have to do that, it's just my own personal convention. So for our deep neural network, we'll start with a dense layer with a ReLU activation. second dense layer with value activation, and an output that will be single valued with no activation. Now keep in mind, one interesting thing about TensorFlow 2 is that we don't have to specify the number of input dimensions. It infers it from the inputs. That's a pretty nice feature. So now we define our feed forward. In this case, we call it call. That'll allow us to use the name of an object as a function call, basically. We need a state and action as input. We'll have a Q1 action value. And we will want to concatenate our state and action along the first axis, and we will feed that through FC2 Q1 action value, and then pass it through the final layer, action value, and return. Now keep in mind that the critic evaluates the value of both the action and state, so that's why we have to concatenate the two values. That is it for our critic network. Very, very straightforward. Next, we're going to handle our actor network, and that again derives from keras.model, just the same as the critic network. Our initializer takes dimensionality as input again as well, number of actions, and you know what, I'm sorry, I'm checking something here. No, I did not. For a second there I thought I passed in input shape to the critic network. That would have been totally unnecessary. Checkpoint directory equals temp TD3. We want all of the models to live in the same directory. Very, very helpful. And then we can go ahead and start saving stuff. And I'm looking at this, and as I look at what I'm doing here, so I like to modify stuff on the fly. I don't think I actually need this and actions here, so let's go ahead and delete that just for the sake of cleanliness. We will need it in the actor, of course. Yeah, let's keep it nice and clean. Model name, checkpoint directory, plus TD3, and just for clarity, that name will have stuff like target actor, target critic, actor or critic, so we can keep all of those particular networks straight. And of course the two critics will be critic 1 or critic 2, because we have very interesting naming conventions. So now we'll have our deep neural network, again a simple dense layer with value activations for the first two layers, and then mu for our output, and that will take an actions as our output dimensionality with a tan hyperbolic activation. The tan hyperbolic is bound between -1 and +1. If you want to take into account boundaries of actions that are beyond +or-1, you can multiply this output by the maximum bounds for your environment. So some environments will have a max action of +or-2, which of course +or-1 is oftentimes less than 2. So you have to take that into account depending on the environment. So again, we need a call function to handle the feed forward. So we'll pass our state through the first fully connected layer, second fully connected layer, and pass that through the final layer and return it. So that is it for our actor network. Next, we need an agent class to tie everything together and to handle all of the really interesting functionality. So our agent doesn't derive from anything, but our constructor is going to take a whole slew of inputs. So we need a couple different learning rates. Reason being, you want to accommodate the capacity for different learning rates for your actor and critic networks. Sometimes they learn best with different learning rates. Input dims, you'll need that for your memory. Tau for your soft update rule. Your environment for a number of important variables from the environment. Default gamma of 0.99. The update actor interval will default it to every other iteration. A warm-up of 1,000 steps. Just a default value for n actions. Max size of 1,000,000 transitions. Layer 1 size 400, layer 2 size, that's our FC1 and 2 dims respectively. A batch size default of 300 and a noise of 0.1. Let's go ahead and start saving stuff. Since we will be adding in noise, we're going to have to perform clamping on our actions to make sure that the actions, the action plus the noise, don't fall outside the allowable bounds of the environment or below. We'll need our memory. That's a replay buffer. Then we need batch size. We'll need a learn step counter. We'll need that because we're doing the delayed part of TD3. We're going to delay the updates of the actor network every 2 different iterations of the update of the critic network to give the critic network time to converge. Then we have, you know, I'm looking at my cheat sheet here. Oh, a time step. Why do I have a time step? Excuse me one moment. No, I believe the time step is for the warm-up procedure. We shall double check that later. If not, I'll come back and delete it in the GitHub. And we don't want to forget number of actions. Sorry, I write this code, you know, sometimes well in advance of doing the video because I get distracted by other stuff. And so when I come back to it, I don't always know what I was thinking. That is the benefit of comments, which I don't really do for this stuff. Sue me, I probably should. We do need our update actor iteration, and that is update actor interval. Excuse me, let me close my door. My toddler is rampaging. And next we can go ahead and start defining our actors and critics. And so the name will just be actor because we are quite creative. To maintain compliance with the PEP8 style guide, let's go ahead and delete a couple spaces. Critic 1 is a critic network. Layer 1 size, layer 2 size, and we don't need number of actions there because I deleted it. So its name will be critic 1. Likewise for critic 2. And again, the purpose of this is to handle the double Q learning update rule. Next, we will need a target actor. Layer 2 size. Let me go ahead and delete the spaces. Oh, you know what? Silly style guides. And finally, a name of target actor. Then we'll need target critic 1. With a very original name of target critic 1. Similarly, target critic 2. And that is it for our networks. Next, we have to compile them because this is a TensorFlow 2. And that is where our learning rates come into play. So we will use our atom optimizer with the learning rate defined by alpha for our critic. Our loss would just be a mean, and our critic 1. Learning rate of beta, a loss of mean squared error, and critic 2 have to do the same thing. Learning rate equals beta. Do I need? Yes, I do. I do need parentheses there. Mean squared error. And then we will handle our target networks next. That is a tongue twister. So we have to compile the target networks just by convention with TensorFlow 2. We're not going to be performing any stochastic gradient descent or atom in this case on those particular networks. We're going to be doing the soft network updates, but we still have to compile them nevertheless. That is just by convention. Rate of alpha loss equals mean. Target critic 1. Okay, so that is all of our networks. Self.noise we'll keep track of as well. Update network parameters with the default value tau equals 1. I do that because on the first step of the update, we have to set the values of our target networks equal to the starting values of the online networks. And so we pass in a value of tau equals 1 to perform an exact update or a hard update instead of a soft update. We'll handle that function toward the end. For now, I want to get to the choose action, remember, and learn functionality because that's where all the really interesting stuff is. So let's go ahead and choose an action based upon an observation of the current state of the environment as input. So if our time step is less than our warm-up period, yeah, that's why we need the time step to handle the warm-up, as I suspected. Glad I didn't delete that. We're going to select an action at random with just a normal distribution with a scale defined by our noise parameter in the shape of number of actions, comma, so we get a batch there, an array of scalars. Otherwise, we want to go ahead and convert our state to a tensor and add on a batch dimension. That's just the way that the inputs are expected to be fed into the deep neural network. We have to add that batch dimensionality. And I have TF float 32 here. It must be due to some sort of precision thing that makes TensorFlow happy. So then we want to pass our state through our actor network and receive our mu. And we're doing that because it returns batch size of 1, want scalar. Then we'll say mu prime, which is where we handle the noise, equals mu plus np random normal, scale equals self.noise, and mu prime is tf clip by value, because again that noise could take us outside the bounds of our environment. So we'll clamp mu prime between min action and max action. Increase our time step by 1, very important, and we want to return mu prime. Okay, that's it for our choose action. Now let's handle the simple interface function to remember a transition. So remember state action reward new state done, and we'll say memory.store transition state action reward new state done. And that's just because we have to interface with the memory in some way. You don't want to have the agent class calling. You don't want to have the agent class interacting with private variables from your memory. That would be poor software design. So next we handle the most interesting function in the whole program, which is the learn function. And the very first thing we want to do is say, hey, if we haven't filled up at least batch size of memory, we probably don't want to be learning. So we'll say self.memory.mem counter is less than batch size. Now, if it's not greater than the batch size or equal to, go ahead and return. Now, since we're doing a warm-up, that won't be the case because the batch size is just a few hundred. The warm-up is 1,000. So by the time we get through the warm-up, then we're already well into filling up the batch size of memories. But if you decided not to do a warm-up, then that would be important. So we'll start by sampling our memory. Self memory sample buffer, pass in our batch size, and then we want to convert all of those to TensorFlow tensors. And I have to be very pedantic with data types here. I think there could be issues if you do not. As I recall, I think it barks at you about data types because it expects certain types of floating point variables in some places and other types elsewhere. And we don't have to convert the duns to a tensor because we're not sticking that in a deep neural network. We're just using that as a multiplicative factor, so we can leave it as a NumPy array. Now we're going to handle our update to the critic network because we do that every time step, and then we'll handle the update to our actor network. So we'll say with TF gradient tape. I have persistent equals true. Oh, because I have two different networks. Yeah, so you need two different. If you're using two different updates for one, if you're using two different apply gradients for a single tape, then you need to pass in the persistent equals true variable parameter, or argument. Otherwise, you don't need that persistent equals true. You just have, say, a single network that you're performing an update on. So we want the actions according to our target actor for the new states. And then we're going to go ahead and add on a noise parameter to that we're going to clip between the range of -0.5 and +0.5. So clip by value np random normal 0.2 minus 0.5. 0.5, and then we're going to go ahead and clip that again because, again, the addition of that noise could take the action outside of the bounds of our environment. And then we're free to go ahead and start calculating our critic values. So Q1 underscore, the critic value according to the first target critic, is the feed forward of the new states and target actions through the first target critic. Q2 underscore is very similar. It's just the evaluation of the new states and target actions according to the second critic. Now again, we're going to have to go ahead and squeeze that output. And the reason is that our shape is batch size by 1, want to collapse to batch size. And we have to do that for Q2 as well. Q2 underscore. And then we're going to need the value of the states and actions the agent actually took according to the regular critic 1 and 2 networks. So we'll call those Q1, And we'll just go ahead and squeeze those right away. Critic 1 states actions squeezed along the first dimension. Critic 2 states actions 1. And then we're going to say that our critic value for the new states is the minimum of Q1 underscore Q2 underscore. And then we're going to need our target value, the Y from our paper, rewards plus gamma times critic value times 1 minus dones. That will set the value of the second term here, gamma times critic value. There should be an underscore there, sorry. To 0 everywhere the done flag is true. And then we have our losses. So critic 1 loss, Keras losses dot mean squared error between the target and Q1. Mean squared error target and Q2. So that is it for the calculation of the critic losses. Now we have to handle the calculation of the gradients. Now we don't have to do anything special for that. The TensorFlow package handles that for us. So tape.gradient, the gradient critic 1 loss with respect to the critic 1 trainable variables. So that should be dot, not an underscore. I make that mistake frequently. Critic 1, critic underscore 1 dot trainable variables. Yeah, that is right. And then we need the critic 2 gradient. Critic 2 loss, self.critic 2 trainable variables. Same deal. Then we need to go ahead and apply those gradients. So calling our optimizer dot apply gradients function, and that expects a zip as input. We're going to zip the critic 1 gradient and the self critic 1 trainable variables. Same thing for critic 2. Optimize to gradient okay. And then we want to increment our learn step counter because that gets incremented every time we update our critic networks. And then we have to address the question of, is it time to update our actor network? So we'll say if that learn step counter modulus self.update actor interval iter, is not equal to 0, then return. So if it's not every n steps, then go ahead and return. And if we haven't returned, then we're going to go ahead and calculate the loss for our actor network. So with TF gradient tape as tape, and here since we're just dealing with one loss, we don't have to call the persistent equals true. We don't have to pass in the persistent equals true argument. So we'll say our new actions are the actions chosen by the current parameters of our actor network for the current set of states. The states the agent saw along the way. The critic 1 value is self.critic 1 of those states and new actions. And then our actor loss goes negative TF math reduce mean critic 1 value. And this may look a little strange to you, but this is how we're going to handle the gradient of the output of one network with respect to the parameters of a network. It's kind of like how you apply the chain rule to the loss of the output of the critic network with respect to the parameters of your target actor, your actor network. Sorry. I hope that makes sense. So then we do the same thing where we calculate our gradient tape.gradient. Sorry, tape.gradient. Did I call? Let me make sure I didn't make a mistake. I did make a mistake up here. Sorry. So this should be tape.gradient, not TF. That is one less error to worry about when we get to running the program. Sorry about that. So tape.gradient, actor loss, actor trainable variables. I'm going to step our optimizer by applying our gradients. Again, that takes a zip as input. Actor gradient self.actor trainable variables. Okay, so then finally at the end of the learning function, we want to update our network parameters. Okay, so that really handles all of the learning algorithm for our agent. All that's left now is to update our network parameters and then handle the model saving. So just a few functions left, and then we can go write our main loop and see how it does. So network parameters. So we're going to pass in a default value of tau for none. Remember that at the top of our the end of our initializer, we pass in tau equals 1 to handle a hard update. Every other time we're going to pass in a none. So we'll say if tau is none, then tau equals self.tau. So every time other than the first time we call this, we're going to use the stored value for tau. So weights equal an empty list, targets equals self.target, actor.weights, for I, weight in enumerate, self-actor weights, weights.append, weight times tau plus targets sub I times 1 minus tau. There we go. And then self.target actor.set weights, and I am going to yank this and paste again, and then say target critic 1 self.critic 1 weights set weights. Sorry, I forgot to set the actual value of the weights. How sloppy of me. And then say self.target critic 1 set weights, and then we have target critic 2 enumerate critic 2 weights.append, and then self.target critic 2.set weights. And that handles our update rule for our two networks. Sorry, my numlock key is off there. Okay. So if it isn't clear what's going on here, we are iterating over the weights of our actor and critic 1, critic 2 networks. Then we're doing the calculation for the soft update rule, saving that in a temporary list and uploading that list to the target actor or target critic 1 or critic 2 networks. Now we can handle the save model functionality. This is the easiest part of the whole project. So print saving models, just a little debug statement to let us know something is going on. Save weights self.actor.checkpoint file .critic 1 checkpoint file checkpoint file. And then we have our target networks as well. Good grief. Then we do the inverse operation of loading our models. Self.actor, load weights from the actor checkpoint file. Then we have critic 1, load weights. Self.critic 1.checkpoint file. And then we have our target networks. I should have chosen shorter variable names to save my wrists a little bit of work here, but hindsight is always 20/20, I guess. Target critic 1 checkpoint file. Okay, so that is it for the main code for our TD3 algorithm. Now we get to handle the main loop, so let's go ahead and code that up. Of course, before we can, I have an invalid syntax right here at the very beginning. TensorFlow.keras.layers. Oh, sorry, that's because it's a from. Import dense. I'll have to notate that in the video. And I have another issue here. Def store transition. Where is it unhappy? I am missing a comma, of course. And I have another issue. OS path join name equals. Yeah, my wrists are non-functional today. Self.targetActor.setWeights. Oh. Why did that happen? Interesting. Did I type those at the end and have a stroke or something? Don't remember it. Very strange. Okay, unexpected. End of file. Let's delete there. Same. Am I forgetting a parenthesis somewhere? I am. Because I have right there. All right, finally. Good grief, that's a whole lot of typos. Now, some people suggest that I upgrade my Vim to actually catch that stuff on the fly, and you're absolutely right. I'm going to do that when I finally force myself to do it. Let's go ahead in the meantime and write our main loop. So we want to import gym, numpy. We'll need our agent, and we'll need our utility file. Plot learning curve. You can do a git clone on my GitHub to get that. It's just a matplotlib pyplot with some labeled axes where we're taking an average of the previous 100 games running. I don't include that in all my videos. I just kind of reference my GitHub. You can just do a plot if you wish. Name equals main. Gym.make. We're going to be doing the Bipedal Walker v2, and we're going to call our agent constructor alpha 0.01, a beta of 0.001. Our input dimensions will be determined by our environment, so we don't have to hard code anything. A tau of 0.005, pass in our environment. Batch size, I have 100 here, equals 400, 300, and actions determined again by our environment. We'll let this bad boy play 1,000 games, and we'll call our file name plots plus walker underscore. Now keep in mind you have to do a make dir plots and a make dir temp slash TD3 to correctly execute the code, because it'll expect that those directories exist. Pass in number of games as a variable for your file name. That way, if you run it over and over again with different numbers of games, it won't overwrite the same plot. You can also include things like learning rates as part of your variable name for your file names. I recommend doing that. I'm just not doing it here. So we need to keep track of our best score. It's the minimum score of our environment. And the reason is we want to save our best models. Keep track of your score history. If you want to load models, now is the appropriate time to do that. Actually, you know what? There may be an issue where we have to actually instantiate our network with some variables to load the models. Open up an issue on my GitHub if that's the case, and I will write the correct code. I won't bother with the video. I'll leave that as an exercise for the viewer, but if it turns out to be a problem, raise an issue and I can fix that. Not a huge deal. Let's go ahead and play our games. Start by resetting the environment at the top of every episode. Reset the done flag and 0. And let's play our episode. While not done, action equals agent dot choose action based on the observation. Let's take that action, get the new state, reward done, and debug info from our environment. Call our learn function. Keep track of our score and set the current state to the new state. Very important. If you don't do that, nothing is going to go well for you. Let's append our score at the bottom of every episode and calculate our average. Minus 100 onward. If our average score is greater than our best score, then set the best score to that average and save our models. And then we want to print some debug information. Episode I, score 1F, average score, average score. And at the end of all the games, let's go ahead and handle our plotting. Our x-axis is just the number of games. And call plot learning curve. All right, so moment of truth. Let's go ahead and see where I have my invalid syntax. I forgot an addition sign there. Very simple. All right, let's try it. You know what? I'm running it over in this other terminal. And okay, so it saves models. It is learning. That is good to know. Let's do a make dir temp slash TD3. I should already have plots. Python main td3.py. Moment of truth. Okay, so it says actor network object has no attribute checkpoint file. I didn't. Oh, it's checkpoint directory, so that is in TD3 TF2. That is in line 70. So that is here. Okay, try it again. Got an unexpected argument name. That is in. Oh, that's because. Okay, that is in line 48. That is super trivial. It's not name equals, it's name plus. Did I do that down here as well? No, I did not. I'm not looking forward to editing this. This is going to be a lot of work. Okay, so it saves models right off the bat and starts running. Okay, so I'm going to let this run for a while, and then we're going to see how it does. Okay, so I did something very stupid, and I let it run and noticed it wasn't actually learning, and so that's a problem. And the reason it's not learning is because I forgot to store the transition. So we have to say agent remember observation action reward observation underscore and done. Okay, and then I got to get rid of the print statements I stuck in here for debug purposes because I'm a noob and use debug statements. Okay. Now let's do Python main td3.py, and now it should work without any funky print statements. Okay, now I'm going to take off for a little bit and see what's going on. And the reason I noticed this wasn't learning is because it was executing much too quickly. It blasted through 350 games in just about a minute, which tells me it's not doing anything useful on the GPU. So I'm gonna let this run. It'll probably take an hour or two, and then I'm gonna come back and see how it did, and we'll take a look at its performance. Now here we are. It's the next morning. This took around 6 or 7 hours to run, so I just waited until morning to film this. But in typical Phil style, the file name for the function call for the plot learning curve function has a typo in it, and so we don't have an actual plot from the performance of this particular run. However, I will show you a plot of a similar run where it achieved an approximately similar score. You can see that it does indeed learn. It achieves a high score of around 285, 288, about 290 or so depending on the run. You get some run-to-run variation. And 300 is the highest possible score you can get for this environment. So I would consider this pretty much strong evidence of learning. It's not a world-class result, but that's not what we were aiming for anyway. We just wanted to understand the gist of the algorithm and implement it correctly and demonstrate that we do in fact understand how it works. Mission accomplished. You can pat yourself on the back for that. I'll also show you some footage of the Walker kind of stumbling along so you can see how it looks once it's fully trained. You can see it has kind of a funny gait, but it does in fact manage to learn to walk. That is pretty impressive, starting from just totally random actions, learning how to walk within just 6 or 7 hours. If only humans were so competent. I hope that was helpful. Leave a comment down below with any questions, suggestions, anything you'd like to see next. Give a thumbs up, a subscribe if you haven't already, and I'll see you in the next video.